Today we're going to talk about branchless programming. Branchless programming is a technique of programming which attempts to take pieces of code that are particularly hot in the execution of a program and remove or at least minimize the number of conditional branching instructions that are contained within this specific piece of code. Branchless programming is often seen as an optimization technique, but among some people it's often a virtue to see how much code they can write branchless as a sort of mental exercise. So today we're going to talk about what is branchless programming, why it's useful, and why you don't need it, and why you probably don't want it as well, actually. Possibly controversial, the last one, but some of this is just my opinion on the subject. But it would probably help before we can talk about branchless programming, what a branch actually is. So we're going to start out by exploring what actually is a branch under the hood and what it is at a high level. So what you can see here is a basic piece of C. So you can see that we have some if and we have some else statements and everything of the like. So if we look at this example of a flowchart here, what we can see is that we take in three variables, a, b, and c. If a is greater than b, we can see our first branch here. Then we check if a is greater than c, that's our second branch here. And then I've done a slight optimization here. I should have probably just left it even more naive than this. But because these two branches converge on the same place right before stopping, these just jump out early and execution just falls down to this here if all of these branches fail. So essentially these two branches have been combined into one here. So when we talk about a branch, what we're essentially talking about is one of these turning points on a flowchart, a location where the control flow of a program is changed about, and where the program is able to make a decision about where its code flows to. And so if we run this example, we can see that we get 24 printed out because because the first condition, A is greater than B indeed, and 24 is greater than A, which is 10, so therefore we get C printed out, which is 24. If we were to change this around, let's make it so that B is greater than it, so 11, let's run TCC, it out again, and we still get 24 because 24 is still greater than B. It's not a great example, but you hopefully get the idea about how branching is actually working here. So let's have a look under the hood what's going on. So this is going to show us a disassembly, so let's seek to main. And what we can see here is the assembly dump output of this program. So we can see the stack frame being set up here, and what we can actually see is there are a few things here. Jump less equal to, and jump less equal to again, and we have a few unconditional jump instructions here and jump less equal to. What we're essentially seeing is we have a bunch of instructions jump, and these are called conditional jump instructions. And what they do is the CPU checks the condition based on the compare instruction that occurred previously, and based on the operand suffix, or prefix in this case I think, of the jump instruction, the CPU will check certain flags in its flags register to see whether this compare instruction has had the effect that's needed for this jump to execute. So jump less equal to will check the negative or zero flags, I think. Basically it checks the sign bit and it checks the 0 bit in the eFlags register. And if either one of those is set, then we can guarantee that the operand was less equal to, and so this jump will execute. If neither is set, however, the code after it will execute, as assembly is executed in a top-down order. And so we continue executing, and these jumps will move us around, and then we have some unconditional jump instructions here to tear down our block. And so when we're in one block here, we don't want it to call code that is outside here, so we don't want to call this code inside this else block if this if block executed. That's not what we want. So this is pretty simple code, and I've intentionally used the tiny C compiler so that there's no GCC shenanigans going on with optimizing out these if statements and making it branchless or whatever. But essentially what's happened here is we've inserted a bunch of jumping around the code where the CPU's changed its instruction order from a linear sequence downwards to a disjointed sequence. We can see the arrows that Radari has inserted for us here to show us where the CPU is going to be jumping to. And so this vaguely follows the pattern of a flowchart, and so that's why I brought up this example of a flowchart here, because it pretty closely models what's going on under the hood. So you might be thinking, this seems pretty simple then. What is the problem, therefore, with using branching instructions? They don't seem like they could have a performance hit. Literally, it'd be about one clock cycle, maybe at the most. I'm not an expert in how clock cycles work, but You see, we will have a memory access here, we have a memory operand, but given that it's local data on the stack, it's very likely going to hit our first level cache, so it's not even got the latency of one memory access. So what gives? What's the problem here? The problem is the modern day architecture of a CPU, in particular instruction pipelining. So instruction pipelining in CPU design essentially makes it so that the processor, while it's waiting on a more latency heavy instruction, will attempt to keep the processor busy, as it says here, by performing incoming instructions in sequential steps, but it reserves the right to perform them out of order. So let's say that we had some expensive operation like a floating point square root, or even just a floating point divide is pretty expensive sometimes, and so the CPU is waiting for the floating point coprocessor, the FPU, to finish dividing or square rooting or doing a cosine of or whatever the operands that we provided it. But it notices that afterwards the instructions that we have are not actually waiting on any previous data. So why can't it just perform these either in parallel or perform it out of order so that the instructions after it are able to be executed similarly? Essentially, it's a sort of look ahead where the CPU can look ahead at the work that it has to do later and perform it already so that it's waiting for it to use later. And so the results of these, even if they are changed by later changes to the previous data, can just be discarded in worst case scenario, and the CPU just does the work all over again. And so the CPU is able to predict what's going on, and it's able to perform instructions out of order so that we can have higher performance in a sequential list of instructions, as machine code is. However, there's a catch. The CPU often has to detect things, and it probably says in the hazards section here, detect things such as dependency chains, where there are a long list of instructions, all of which rely on the fact that each one is executed in order. And a good example of this is, for instance, mutex locking. Mutex locking needs to ensure, and we do this with things called memory barriers, partly so the compiler won't mess us up, so that the CPU will execute these instructions guaranteed in order, rather than, while we're waiting for the mutex to lock, just performing the critical section out of order. That would never make any sense. Instead, we have to wait on the instruction with a lock prefix, it's called, so that the CPU can perform an atomic operation after the core has finished operating on that memory address. And once this occurs, we're able to then move on to access the critical section and mutate the shared data structure or whatever. We cannot have the instruction performing this the CPU performing this out of order. Another big issue, however, is the fact that branching instructions, in their inherent nature, are reliant upon the data which occurred before them. And so the CPU has a small workaround for this, and it's called a branch predictor. And a branch predictor essentially looks at the branch, and it says, is this likely to happen? If it is, let's take the branch and let's execute these instructions, assuming that they're going to work, and that these are going to be the instructions that are going to be finally needed at the end. If the branch is unlikely to be taken, then the CPU will instead ignore the conditional jump instruction and will instead do pipelining and look ahead on the instructions that wouldn't be taken by this branch. So if we go back to our C example, if the CPU determines that it's more likely that A is larger than B is larger than A, then it will do pipelining on these instructions and it will look ahead on these. And if it determines the opposite case, then it will instead perform these instructions. And this is a very clever situation for us to find ourselves in, because we have a way to optimize the performance gains of our branch predictor. So I come to the same question yet again then. So why is there all the hate for branches when it seems that we have a branch predictor? The clever engineers at Intel and AMD have already managed to solve this problem for us. Why am I obsessing then over this seemingly solved problem yet again? Well, if we read the Wikipedia article a little further, we'll discover that actually there is not really any branch predictor in existence that is able to 100% accurately predict branches. And so branch mispredictions can actually become a bottleneck for specifically the instruction pipeliner when we're attempting to take advantage of it for a performance gain. Branch mispredictions are actually a metric that you can track in the Valgrind performance counter. And so it is something actually that does have a noticeable impact on performance in particularly hot pieces of code, pieces of code that are being executed particularly often and in very large quantities. And so obviously with anything like that, it's something we can optimize. And the simplest way of doing this, and the most portable for that matter, is to simply remove the branches altogether. There are other ways of optimizing this, and if you look in the Linux kernel, you'll often see at conditional branching, you'll see things like unlikely or likely placed before it. And this is also often done in, for instance, game engines who need to be able to perform many conditional branching instructions every frame without them being a bottleneck. They're able to tell the CPU implicitly by hinting to the compiler how it should format its code to basically influence the branch predictor to take a certain branch over another based on the fact that the programmer knows which one is more or less likely. And so the hate for branches comes almost entirely from the problem of branch misprediction. And so it has everything to do with the way that the CPU's pipelining works. So, not all equivalent solutions to the same problem are made equally. Generally, the more concise solutions are quote-unquote better. They're nice and easy to read, and often they generate less code under the hood, and less code is obviously faster to execute. Or, in theory it is, of course. The floating point square root operation is obviously another an example of a place where it isn't. The fast inverse square root, just performing a 1 over on it, is it's far. I think it's probably faster in general when using integers. Or it uses floating points in general. It's breaking my brain again thinking about CPU cycles. Anyway, more concise solutions are often better, and so it's often seen as a virtue to manage to write something in a particularly elegant branchless way. There is, however, a big but to all of this. It might sound brilliant. You might think, oh, okay, I'm going to go and tear out all of the if statements from my code. I'm going to go and remove all of the switch cases. And before we go any further as well, I should make it clear that conditional branching instructions also occur in conditional loops. So that's for loops, that's while loops, do while loops. The exceptions are loops where the condition is always true. It will be optimized out, I reckon. And in languages like Rust, where you have the loop keyword that performs an infinite loop, then I would assume that under the hood that uses unconditional branching. But conditional branches don't just occur at if statements; they occur at switch statements as well. All of this uses conditional branching, but there's a big but to all of this, and there's quite a few drawbacks. And the first one is actually the most detrimental, and that's that the compiler's smarter than you, the CPU's smarter than you, basically everybody's smarter than you. In fact, we can probably say that. When you use common idioms in C, like this if here, if I was using a smarter compiler unlike TCC, which I've intentionally selected for this purpose just so I know that it's not going to optimize out these if statements, there are actually machine instructions that are very efficient at doing this in hardware that GCC could choose to use if it recognizes this idiom. When it sees an abstract syntax tree and it goes, we have a comparison or an alternate comparison, we have like a double comparison here, I could replace this using the compare and exchange or whatever. Another good example is, for instance, if we have a function, let's just make it void for now. The classic example I was taught in school of the compiler optimizing things for you is if we have int a and we need to try and exchange, so let's do int pointer a, pointer b. And then let's make this C, and we need to try and exchange these two from each other. Well, what I was taught in school to do is you do C equals the value of A, the value of A equals the value of B, then the value of B equals C, because we've stored in the value of A here. The compiler can recognize this as a common idiom that could be sped up, and it can use either the XOR trick, where you can XOR together these two in a specific pattern and swap around the bits in each, or it can even use simply the exchange instruction in x86, which will actually do an atomic exchange between these two in a single machine instruction. And so there are lots of clever things that the compiler can do to optimize your code for you. And so that it is more than likely that the compiler knows better than you in a specific situation, and actually writing naive C code will actually result in a better program than writing very clever C code. And as people were pointing out in the Strelen video quite often, it's quite common that compilers can recognize things like misuses of strlen and, you know, loops that are being made over n squared by accident because the person doesn't use C strings correctly. It's very common that optimizing compilers can cut these out for you, because optimizing compilers are a very, very clever invention. So what we have is a situation where if we optimize, we might get better code, but if we don't optimize, then we might have it that the compiler writes better code for us. And so if you really, really need this performance to get really, if you really need this performance this much, the actual good way to do this is to simply write the assembly by hand. Obviously, you lose portability then, but I think that there are some ASM compilers that can transpile between different assemblies if, on the fly. I think NASM can do that for you. There's a few of them that can do this, and if you have code that's that hot, it's been called like thousands of times a millisecond, then that's the situation when you're going to want to do this kind of thing. It's arguably the only situation. The situation where you're going to need to the situation where you're going to need to micro-optimize to this degree is probably the situation where it calls for assembly. And so it's a kind of damned if you do, damned if you don't situation. If you don't, the compiler might write better code for you. It might just decide to hell with it and not in the moment. We can't trust compilers. They are not our friends. And you're probably better off writing assembly if you really need this sort of micro-optimization. It says here branchless and micro-optimization. I've practically covered this already, but micro-optimization is probably one of the things that's going to overcomplicate and bloat your code base more than anything else. It's very difficult to strike the correct balance, because branchless trades reliability for performance, or readability. Sorry, not reliability. So this is something I notice quite often in C++ template code bases, where templates are technically superior to runtime selection based on the type assertion, for instance, in Go, because it generates a distinct piece of code for every single type that is referenced in this code base. So every time you reference, for instance, standard vector for a specific type, it generates a unique standard vector class which is optimized separately for each case of the specific object. So standard vector of int is different to standard vector of long, stuff like that. And so the C++ STL, I think that templates are actually quite unreadable and they make it very difficult to understand more complex code with them, but they do increase performance and they are technically superior. And it's similar to branchless programming in that respect, in that it trades the readability of your code base for performance. And this is something where we had to hark back to the old rule that developer time is very important. If you're spending all of your time trying to work out the best possible algorithm to exchange two values between each other, you're probably being counterproductive. The example I showed a minute ago, using a temporary variable, is more than sufficient for about 90% of applications, and there's no problem with using it. And so branchless programming and like the XOR trick for exchanging things, or just inserting inline assembly to exchange things, all of these are micro-optimizations before you know where the hot pieces of code are, before you know what the bottleneck is, and before you know what you actually need to optimize. And that's probably one of the biggest problems in optimizing code today, that people have difficulty finding what's actually needed to be optimized. You have to weigh up how hot the section of code is and how you actually need to optimize it. In game engines, if something's being called like 100 times every frame, yeah, go ahead and make it branchless. It can't hurt, and even then you should be running it through Hyperfine and like optimizing it using whatever tools, Valgrind or whatever that you have, and only if you've determined as well that branch mispredictions are actually causing performance hits, and you can do that using Valgrind yet again. So, now let's look at some examples. So you might have seen me flipping between these two tags here. So this is the one with the assembly output, and this one here, what we're going to do is we're going to write an algorithm, and this is going to be a pretty simple algorithm. What it's going to do is it's going to find the remainder between this value divided by 10. So what we're going to do is we're going to, first of all, let's just declare res for result. All we're going to do is res equals target and then the modulus of 10. So this is pretty simple so far. Let's just return res. Okay, and so there's one key catch though, and the catch is going to be that the value can never be 0. So if it's a multiple of 10, the value needs to be 1. So basically we need to add 1 if res is 0. So there's two different ways we could go about this. We could go about this the branchless way, or we could go about this the branched way. And this is obviously a pretty simple, naive example, but it serves to illustrate well the way that we can eliminate branches with some clever tricks, specifically in C. So what I'm actually going to do is I'm going to do for, and then actually I'm going to have to include limits.h. In fact, let's get rid of math. I was going to just do 2 to the power 32, but let's do int I equals start at 0. I is less than int max, and then just I++. And then you'll notice that we've already got a conditional branching instruction actually, so you know we're doomed before we've even started here. But this will be constant between the two examples, so it won't affect our benchmark. And what we're going to do is we're going to do res, and then we're going to printf the result of algo, and then the algo is going to run on I. Okay, and we have an error here because I put a comma instead of a semicolon. And so if we run bench now, it's taking quite a long time. I might actually have to bump down the actual number of numbers that we're taking to do this. So let's instead do it short max. Let's run it again. And now it's taking a reasonable amount of time. We're actually being able to get a benchmark of it. Let's just check that it is actually, yeah. So at the moment we're still returning 0 for some values. As you can see, if we run it, we have a 0 right here. But we've successfully clipped it so that the values are between 1 and 9. And so our algorithm is somewhat working as expected. But what we have to do now is if res equals 0, or alternately we could do if exclamation mark res in C, and then whoops, res plus plus. And so this is our branched way of doing it. So if we run this again, there's not been an enormous difference. In fact, there's been pretty much no difference at all. What we can now do, however, is we can rewrite this piece of code so that instead this piece of code is actually going to run branchless. So what we can do is res is going to be equal to, and we're going to add to it. In fact, we can't do it on one line, but we'll do res plus equals, and then res is greater than 0. And so this is going to remove the conditional branching instruction. What's going to happen is res will be set to some value, and then if res is greater than 0, this will be if this is equal to 0, this will be equal to 1, and then we're going to add this value to res. So we'll increment it if it's equal to 0. We could even do better here, and we can remove the dependency cycle, and we can do if target %10, so the modulus of 10 equals 0, and we could even therefore place it on one line. So do this, and if we run this now, we can see we have actually got we've got a change in the time that it took to execute. It's actually gone down from 2.1 milliseconds to just 1.4 in just having run this this small micro optimization in this specific callback, because this is really hot code. This has been called really often. So unless I'm being stupid, I think that was a good example of micro optimization actually helping us because of branch mispredictions not being a factor in this problem. Because you'll notice as well that that branch that we placed in there was actually the unlikely case. The unlikely case was that branch would be executed, so when it got mispredicted, we were throwing away performance. And so that was what I think was a good example and a benchmark to demonstrate what I'm talking about. So hopefully now you can go forth and understand exactly what's going on in branchless programming, what all the seniles are complaining about, and you can tell people with a big smile on your face that you have written a whole algorithm with no conditional branching instructions in it, and boast about how you've achieved a 0.1 millisecond increase in performance. Thanks for watching, hope you enjoyed. See you in the next episode of Teaching C.